Alright, hi. So today we're going to be going through the Unit 2 chemistry paper from AQA, and this is the May/June 2014 paper. This is the higher tier, so some parts won't apply to you if you're taking the foundation tier, but we will be going through the whole paper as usual. If I'm going too fast or you need to go over something, please feel free to pause and rewind the video as you like. But let's kick off straight away and jump into question 1. Alright, so here we are told that the label shows ingredients in a drink of cola, and A part 1 says the pH of carbonated water is 4.5 and the pH of cola is 2.9. Name the ingredient on the label that lowers the pH of cola to 2.9. So this is going to be obviously an ingredient aside from carbonated water, because that goes down to 4.5. That makes the pH even lower. A low pH is indicative of an acid, and we can see straight away here that we have an acid, and it is phosphoric. So phosphoric acid is our acidic ingredient. Next, which ion causes the pH to be 2.9? Well, which ion causes anything to be acidic? It is the hydrogen ion, which is H+. You could have written hydrogen ion as a word, but H+ is the more correct. If I wanted to be really picky, I could say H+ aqueous, but they're not going to be as picky as that. Alright, let's move on. 1b. So B, part 1. Here we have a student investigated the food colouring in cola and in a fruit drink using paper chromatography. The chromatogram in figure 1 shows the results, and you can see them here. In cola we've got these 3 dots, and in a fruit drink we've got these 2 dots. Alright, to complete the sentence, the start line should be drawn with a ruler and, well, you should know that it's drawn with a pencil. For obvious reasons, if you're using pen obviously is using ink, and ink is almost like a dye. It will run just like dyes will and colouring will on the chromatogram on the paper. Alright, so when it says give a reason for your answer, you will say ink will run and cause smudging. Alright, and it's as simple as that. Only 1 mark for pencil and 1 mark for saying that the ink will run. You could have on the flip side obviously said that pencil will not run, and it's exactly the same answer. Alright, suggest 3 conclusions you can make from the students' results. Now let's go back up and have a look at their results. Alright, so it might seem a bit simple, but remember I said that there are 3 dots in cola and there are 2 dots in the fruit drink. That's already 2 points, because I can just say that there are clearly 3 colours or 3 colourings in cola and 2 colours in the fruit drink. So I'm going to say in cola there are 3 colours. Alright, the second one, in fruit or in the fruit drink there are 2 colours. Alright, that's 2 out of 3 marks already, which seems very simple, and it is. So the last observation I'm going to make is this one here. Well, these look like they're at exactly the same place. Now remember how chromatography works, right? The different dyes or colourings or whatever it is that you're separating, they like the paper in varying amounts. So some of them will try to stick to the paper as much as they can, and so they won't move very far from the start line, and so that's like this one. Whereas this one at the top, alright, it's obviously moved really far. That's because it doesn't have a high affinity for the paper, or it doesn't like the paper very much, so it's fine to just run along with the solvent. But bearing in mind these are at exactly the same position, we can say that one colour is common between cola and fruit drink. Or I can say one of the colours is present in both cola and fruit drink. Alright, so let's move on. 1C tells us that caffeine can be separated from other compounds in the drink by gas chromatography. Why do different compounds separate in a gas chromatography column? Now, you should remember that gas chromatography basically works on a similar basis, but it's slightly more complex in that the inside of the column attracts or doesn't attract the different chemicals which you're allowing to travel through the column, and they are retained for a certain amount of time. That is known as the retention time, and each substance has a different retention time, and so they separate because different compounds have different, sorry about this handwriting, retention times. Alright, there's a number of ways you could have worded that answer. You could have said that the substances are held in the column for longer. You could have said, also said that they travel at different speeds through the column. Alright, let's have a look at D. Caffeine is a stimulant. Yep, we know that. Large amounts of caffeine can be harmful. Only one of the questions in the table can be answered by science alone. Tick next to the question. Right, the first one, should caffeine be an ingredient in drinks? Alright, now there are obviously various different arguments for that, because some people think caffeine's good, some people think it's bad, and we don't know exactly the right answer to that. So there's going to be loads of arguments. Science alone cannot argue that. The second question, is there caffeine in a certain brand of drink? Now, if we take a certain brand of drink and we run tests on it, we can determine exactly how much caffeine there is in that drink. So this question sounds like it's going to get a big tick. And just to make sure, let's have a look at the bottom question. How much caffeine should people drink? Well, that depends on who you are. Right, some people can tolerate a lot more caffeine than others, and some people don't want caffeine at all. Some people want caffeine to wake them up, so that also can't be answered by science alone. All right, good. And now D, part 2. Give 2 reasons why the other questions cannot be answered by science alone. Right, and I basically just went through them there. So the first one should, well, rather than saying the first one, both questions really have similar reasons why they can't be answered. So the first answer really is going to be, well, more than just science-based questions are also related to opinion. Alright, so the opinions of different people are going to vary, and that means that the questions can't be answered just by science. Alright, another one. Well, if you think about it, could you possibly carry out an experiment to tell you exactly how much caffeine people should drink? Well, no, you couldn't, because people is a very broad term, and it depends on what they're drinking it for. So, experiments cannot answer the questions as they depend on scenario and each individual. Alright, there are loads more, obviously, that you could talk about. You could talk about costs. You know, should caffeine be in drink? You could talk about the costs of it. You could talk about the behavioural impacts it has on people, right? There's loads of things that you can go into, but these are just 2 very easy ones that I wanted to cover. Alright, and so that is the end of question 1. Alright, so first off, question 2 says that we are going to be assessed on our English, and remember that this only makes up 1 mark out of your 6. Alright. Explain why chlorine, Cl2, is a gas at room temperature, but sodium chloride is a solid at room temperature. And it says, include a description of the bonding and structure of chlorine and sodium chloride in our answers. Right, so this is basically talking about the overall structure and how all the atoms are held together, or atoms or ions that is, are held together, and obviously we're going to therefore be talking about bonding. Now I'm going to treat these separately. I'm going to use separate colours for both, and I'm going to use purple to talk about chlorine to start off with. Now in this question I'm not going to write in full sentences and paragraphs because it's more useful for you for me to bullet point all the points, but make sure that you're writing in using good English and sentences. Alright, so the first one, chlorine. Chlorine is a covalent molecule. Alright. Now that is literally worth a mark on its own because you've mentioned what type of bonding there is and you've mentioned that it forms molecules, right? So next I'm going to say that simple molecules form very, right, I'm going to underline that just so you know that it's important, very weak interactions with other molecules. And those are intermolecular forces. Right? Alright, these are easily overcome. I'm going to put in brackets here, low energy. So it only requires a small amount of energy to overcome those intermolecular forces. Alright, which therefore equals a low boiling point and melting point. Alright, just so we're clear, for chlorine, bearing in mind covalent bonds are very strong. To turn chlorine into a gas or a liquid from a solid, you don't need to break those covalent bonds, you only need to break the intermolecular forces, right? Chlorine does not have to be broken down into chlorine atoms, it is broken down into chlorine molecules, and the molecules are held together by covalent bonds. Yes, that is strong, but we don't need to break that, so the amount of energy required to turn chlorine into a gas is very, very low, and that's why chlorine is a gas at room temperature. Alright, now I'm going to use orange to talk about sodium chloride. So NaCl, or sodium chloride, is an ionic substance. Okay, ions are held together by strong electrostatic forces of attraction. Forces of attraction. Now, what's important here as well is that these forces act in all directions because, as you can see, if we look at the diagram up the top, I'm just going to point to a sodium ion there. This is a sodium ion, and you can see that here, here, and here are chloride ions. Okay, if we were looking in 3D, there would also be more surrounding it. There's in sodium chloride anyway, there's 6 ions surrounding every one ion. So in 3D, each sodium is surrounded by 6 chlorides, and each chloride is surrounded by 6 sodiums. All right. Obviously, that changes depending on which salt you've got, but in sodium chloride, that's at least true. So I'm going to say that bonds occur in all directions and there we go, and oppositely charged ions are held in place in a giant ionic lattice. Right, that's the name for the structure, the giant ionic lattice. So, large amounts of energy required to break the strong ionic bonds, because in a lattice, the bonds you need to break are the ionic bonds, right? There's no molecules here, so there's no intermolecular forces. The bonds you need to break are the ionic bonds themselves. So to break those, we need a large amount of energy to break the strong ionic bonds, and therefore high boiling point and melting point, solid at room temperature. Okay, so quickly to recap, chlorine makes covalent bonds, it makes simple covalent molecules. There are weak, very, very weak forces of attractions between the molecules, which are easily overcome by a small amount of energy. That small amount of energy is present at low temperatures, and so therefore there is a low boiling point and a low melting point, meaning that chlorine is a gas at room temperature. Now, sodium chloride is an ionic substance. All right, it's held together by strong electrostatic forces of attraction between oppositely charged ions. Those occur in all directions, and therefore there are loads of those forces that need to be broken down. This requires a large amount of energy to break down the giant lattice, and therefore a high temperature is required. So a high melting point, high boiling point means solid at room temperature. All right, and that's the end of question 2. All right, so let's have a look at question 3. We're told that figure 2 represents a reaction in the production of sulfuric acid. Right, and we have sulfur dioxide going into a reactor, oxygen coming in from the top, and sulfur trioxide coming out on the right hand side. Right, and we're asked to complete and balance the equation for the reaction. Now, importantly here, we need to put in a substance because, look, oxygen is added into the reactor. Sulfur dioxide is reacting with oxygen to make sulfur trioxide. So, of course, our substance here is going to be oxygen. All right, and they've given us the state symbols, which is handy. Now, when we come to balance, well, let's have a look. On the left-hand side, we have 1 sulfur, and we have 1, 2, 3, 4 oxygen atoms. So 1 sulfur, 4 oxygens. On the right-hand side, we have 1 sulfur and 1, 2, 3 oxygens, right? But it doesn't give us any room to add anything else on this side, so we just need to balance on the left. So, what I'm going to do is I'm going to say, seeing as we need 1 oxygen, but we've actually added 2 oxygens, I'm going to multiply everything by 2. So I'm going to say 2 lots of these and 2 lots of these give us equal amounts again of sulfur, 2 on the left, 2 on the right. But now we have 1, 2, 3, 4, 5, 6 on the left-hand side and 1, 2, 3, 4, 5, 6 oxygens on the right-hand side. This is now completely balanced. If I didn't want to do that, right, I could have said 1, 1, and instead of times everything by 2, I could have just halved the amount of oxygen. And this is also correct, because now we have 3 oxygens on the left and 3 oxygens on the right. That would still be fine. Because we're given these dotted lines, though, I'd rather put the 2's in there, and there we go. However, either one of those, you would have got the marks in the test. So, 3b, the conditions affect the rate of reaction. The pressure of the reacting gases was increased. State the effect of increasing the pressure on the rate of reaction. Alright, so remember, if you're taking triple chemistry, right, you could actually get confused here. We are not talking about the equilibrium position. This symbol here tells us that this is a reversible reaction, but at the moment we're not talking about changing the yield of anything. We're just talking about the rate, okay? It says here, state the effect of increasing the pressure on the rate of the reaction. So all we're doing here is we're talking about the kinetic theory, okay? So the first thing is that the rate increases. Okay, that's what's going to happen, and that's worth 1 out of 3 marks. Now, how do we know that's going to happen? Because if we increase the pressure, then that means that all the molecules which are going to be reacting are going to be closer together, okay? Because pressure is almost like concentration, but when you're talking about gases. So there are more molecules of gas in the same amount of space. Right, so we're going to say particles, or molecules in this case, molecules are closer together. Right, and so let's just put, well, that's basically a mark. But I'm going to say, therefore, the number of collisions, okay, so collisions between the molecules, is increased. Right, now if I want to be really picky, I would say here, I would say number of successful collisions. Right? It's true the number of collisions is increased, but that doesn't tell us that definitely they're all successful. So if I say the number of successful collisions, because a successful collision means a reaction has happened, right? So because they're hitting each other more often, the chances of successful collisions happening is increased, and so the number of successful collisions is also increased. Now that doesn't seem like a lot of work, but that is 100% 3 marks. All right, moving on. B, part 2. A catalyst is used for the reaction. The gas passes through the gases pass through a layer containing pieces of the catalyst. Figure 3 shows the shapes of pieces of catalyst. Suggest and explain why shape B is more effective as a catalyst than shape A. Now you should remember that something else which affects the rate of a reaction is the surface area, right? This is almost trying to trick you because catalyst is seen as another thing which increases the rate of a reaction. Very true. And so why not the surface area of the catalyst? Because that means it's exposed to more of the reactants at a given time. So the surface area of B is higher than of A. This allows more of the reactant to be in contact with catalyst, which equals increased rate of reaction. All right, that's enough for 2 marks. So let's move on to 3C. The reaction is carried out at a high temperature to provide the reactants with the activation energy. What is meant by the activation energy? Now this is a definition that you just need to know. This is the minimum amount of energy that particles must have for a reaction to occur. You could have said the minimum amount of energy in order for particles to collide successfully or to have a successful collision, but that is because that means basically they're going to react. So the minimum amount of energy required for the particles to cause a reaction to occur is absolutely fine. You wouldn't have to say particles in this case because it doesn't say with reference to the collision theory. You could have just said the minimum amount of energy in order for a reaction to occur, but this is a much nicer definition. Alright then, moving on to 3D. It says sulfuric acid reacts with metals to produce salts. A student concluded that potassium would not be a suitable metal to react with sulfuric acid. Explain why. Now, bear in mind that this means that the student is going to carry out the reaction. Now, from the reactivity series, you should know that potassium sits right at the top. Potassium is extremely reactive, and that's why you barely will ever use it ever at a school, because it is so reactive. Even if you put it in water, you know, it's going to blow up, or it's going to catch fire if you've got a small amount of it, but there's going to be a really aggressive reaction. Put it in acid, and it's even more violent, right? Because an acid is going to react more vigorously than water is. So, I'm going to say potassium is far too reactive meaning the reaction, or per experiment, if this is being done in a school lab, would be too dangerous. Alright, that's absolutely true. It'd be way too dangerous to do that in a school or to do that in any sort of normal conditions because the reaction is going to be so violent. Alright, let's have a look at D part 2. So we're told a student reacted zinc metal with sulfuric acid, which sounds a lot safer, to produce a salt and another product. Complete the equation for this reaction. Well, you should know that when we have just a pure metal reacting with an acid, we are going to get a salt plus hydrogen gas. When we react an alkali with an acid, we get a salt plus water, but because the metal cannot give us any oxygen, right, we're not going to get water, we're just going to get hydrogen gas. And so I'm going to fill in that with our hydrogen gas. Now the metal is going to form a salt with the non-hydrogen part of the acid, and that is sulfate. And so we're going to get zinc sulfate. Alright, and this is already balanced. Okay, it doesn't ask us to balance the reaction because it knows that we're going to be balanced anyway. It's just completely one-to-one all the way across. Okay, so that's part 2. In part 3, we are told the student wanted to increase the rate of reaction between the zinc and the sulfuric acid. State one way, other than using a catalyst, the student could increase the rate of reaction. Now, there are a few here. You should know, we've already gone over some of them in this question, the different ways of increasing rates of reaction. They include catalyst, which we're told we're not going to do. They also involve concentration or pressure. Right, bearing in mind these are not gases anymore, we'll be using concentration. Also involves temperature. Alright, and we've already seen surface area. Okay, so what I'm going to do is I'm just going to say increase concentration of acid. Right, that's perfectly fine. I could have said increase the temperature. That would have been a mark as well. And I could have said increase the surface area of the zinc. And the way to do that would probably be by turning it into a powder or small chips of zinc. And that would have been perfectly fine as well. So 3 possible marks there, but it's a 1 mark question. All right, and that is the end of question 3. All right, so let's take a look now at question 4. So it says, this question is about zinc and magnesium. Zinc is produced by electrolysis of molten zinc chloride as shown in figure 4. And we've got this diagram here which shows the electrolysis setup. For A part 1, it says, why must the zinc chloride be molten for electrolysis? Now, zinc chloride is an ionic substance, and you should know that ionic substances only conduct electricity when they're either molten or they're aqueous. And so what we need to happen is we need the ions to move to their corresponding electrodes. All right, so we're going to say for the ions to be able to move to the electrodes. Okay, just saying so that the ions can move would be enough. Saying that they can carry charge would also be enough. That's only a 1 mark question, so that is fine. Alright, so A part 2, it says describe what happens at the negative electrode. So, at the negative electrode, obviously we're going to be attracting positive ions. And so if we have zinc chloride, right, that is obviously going to form zinc ions and chloride ions, right? So I'll put a plus there. So this is what's going to be formed in terms of the ions. Now those ions are going to move to separate electrodes. Which one's going to move to the negative electrode? It's going to be the positive ion, which is the zinc ion. So what I'm going to say is that zinc 2+ ions move to the negative electrode. Now, what happens at the negative electrode? Well, they're going to gain electrons, right? The electrode is negative, so it has excess electrons, and those are given to the positive ion. So here, it gains, and in this case, we've got a 2+ ion, so it's going to gain 2 electrons. 2 electrons. All right, so it gains 2 electrons, and this is going to form, so forming zinc metal, because now we're going to go from ions to atoms, and if we have loads of metal atoms, obviously we're going to have the substance, which is a metal. Alright, so that's good for 3 marks. Next we have part 3, which says complete the half equation for the reaction at the positive electrode. Well, at the positive electrode we're going to get the negative ions, and remember the negative ions up here were the chlorides, right? So we've got the Cl-. And you'll notice that there's no state symbols on this chlorine, so we don't have to write state symbols for the rest. But we do know that it's molten, so it's going to be liquid. So what we're going to have is we're going to have the negative ions, okay, forming Cl2 plus electrons. But because we have Cl2, we're going to have 2 of them, so we need 2 Cl minuses, right? We cannot write Cl2 minus like that, because these ions are not in a molecule. We just have 2 of the ions like so. And obviously, if we are going to be forming Cl2, right, basically we're going to be losing 1 electron, but from each one of these chlorides, and there are 2 of them. So 1 electron from each makes 2 electrons. Right, let's have a look at part B. We are told magnesium can be produced from magnesium oxide, and we're given the equation for that reaction. How can you tell from the equation that the reaction is done at a high temperature? So we're going to have a look at what is happening in the reaction. There's no other way to tell temperature if it's not given to you, other than making assumptions looking at the states of the compounds or the chemicals. So silicon solid reacting with magnesium oxide solid forms silicon dioxide as a solid plus magnesium as a gas, right? This is ringing alarm bells because magnesium is a metal, and if that metal is a gas, then obviously that is a really high temperature. So what we're going to say is that magnesium is formed as a gas, and that's all we need for 1 mark. Next, we've got part 2. The reaction to produce magnesium from magnesium oxide is endothermic. What is meant by endothermic reaction? Well, an endothermic reaction, you should just know, is a reaction in which energy, well, remember, in an endothermic reaction, the temperature goes down because energy is taken in from the surroundings. So the surroundings themselves cool down. So in which energy is taken in from the surroundings. Alright, part 3. A company made magnesium using this reaction. Calculate the mass of magnesium oxide needed to produce 1.2 tons of magnesium. Alright, so this is going to be a question basically involving moles. Now let's go up and have a look. Well, we can first of all, we don't care about silicon at the moment, right? We're only going to be equating magnesium oxide and magnesium, and you'll notice that they are 2 to 2. So 2 MgO makes 2 Mg, which is handy because that means that they are a 1-to-1 ratio. 2 to 2 is the same as 1-to-1. All right. So what I'm going to say, let's just scroll that up slightly so you can see. There we go. So what I'm going to say is that 1-to-1 ratio, just to remind me. Okay, and we've got 1.2 tons of magnesium. Now, I'm going to just work in tons then, as if this was grams. It doesn't matter that it's tons or kilograms or grams. As long as you use the same units all the way through, then you're going to be fine. So, our molar equation is number of moles is equal to mass divided by molar mass, right? And bear in mind that the molar mass of magnesium is just 24 because Mg is not a molecule, it's just Mg. So number of moles of magnesium, I'll put magnesium here just so you know, equals 1.2, because that's the mass that we have, 1.2 tons divided by 24. And that's going to give me an answer of 0.05 moles. Now remember that we don't equate masses, we equate moles. So that means that in this reaction, if this is 0.05, that means that because the ratio is the same, that means that this is also 0.05 moles. And because these are half, these would both be 0.025 and 0.025, right? Because we have a number 1 in front of these and not a number 2. So they're going to be half the number of moles as Mg. All right. So all that means is that we can say that for MgO, right, I'll just put that in brackets, number of moles, which we know is equal to mass divided by molar mass, right? This still comes from this equation here, N equals M over Mr. Now we know the Mr of magnesium oxide because magnesium is 24 plus oxygen, which is 16, gives us a total of 40. So 0.05 moles is equal to the number of equal to the mass in tons divided by 40, right? And now obviously here to rearrange to get M on its own, I times both sides by 40, so I get 40 times 0.05 is equal to the mass, which is equal to 2.0 tons, right? So the mass of magnesium oxide needed is 2.0. All right, perfect. Let's move on. Now we have B part 5. The company calculated that they would produce 1.2 tons of magnesium, but only 0.9 tons was produced. Calculate the percentage yield. Now, percentage yield is only a 1 mark question, so you literally just have to put the numbers in. is equal to the actual amount. So I'm going to say act divided by theoretical, right? Theoretical amount times by 100, right? So the actual amount was 0.9 divided by the real amount, which was, the actual amount was 0.9 divided by the theoretical amount, which is 1.2, times by 100, right? That is going to give you a total of 75%. And that is it for 1 mark. All right, part 5. Give one reason why the calculated yield of magnesium might not be obtained. Now, there's probably 5 marks you could get here. This is only a 1 mark question, so we only need to pick one. The most basic one that I always come to is the reaction may be reversible. Reversible, right? If it's reversible, it means the reaction doesn't go to full completion, and obviously you're not going to form all the product which you've calculated that you could form, right? Other answers that you could have give would be that other reactions may have occurred. So magnesium oxide, might have reacted in other ways, which meant that the final product wasn't magnesium, and therefore you're not going to get the right amount of magnesium. Some may have been lost, or it may have escaped, right? If you're giving off magnesium as a gas, then some may have escaped, and so you won't have the amount of magnesium that you expected. And you could say that it's impure, so your magnesium oxide or your silicon might have been impure, and therefore your masses that you measured at the start aren't actually correct, because impurities would have messed up those results. Alright, so there are loads of answers for that one, but that brings us to the end of question 4. Alright, let's have a look at question 5. So it tells us carbon atoms are used to make nanotubes, right? We should know that. We've had a look at carbon nanotubes during the course. So it says carbon atoms in a nanotube are bonded like a single layer of graphite. Alright, that's important. Figure 5 shows the structure of a single layer of graphite. And so you've got this ring structure, right, where you have these hexagons and they're all joined to other hexagons, and each carbon, each circle here represents a carbon, is bound to 1, 2, 3 other carbons. And that means obviously we've got the delocalized electrons. All right, let's turn over. 5a says suggest why carbon nanotubes are used as lubricants. Right, obviously a lubricant is there to make things slide over each other. Now the point is that the layers in graphite are able to slide over each other, and if the bonding in a nanotube is just like the bonding in graphite, then you'd expect them to be able to do the same. So first of all, what we're going to say is that the nanotubes are able to slide over each other. Right, and how do we know that they're actually able to slide over the other tubes? Well, if we have a look up here, this tube is basically a self-sustaining object, if you like. If you had another tube next to it, right, if you had another tube which looked the same next to it, those two tubes wouldn't actually be covalently bonded together, right? They wouldn't be bonded together at all. So we're going to say that there are no covalent bonds between, right, and that's important, between the tubes, right? There may be very weak intermolecular forces, right, between them, but there's no covalent bonds, which means they're able to slide. Okay. Next, it says explain why graphite can conduct electricity, and we mentioned this as well. Well, each carbon has a spare electron, if you like. So a pair of carbons will have a spare pair of electrons, right? So those electrons, as we said, are delocalized. So the first point is that there are delocalized electrons are present as each carbon bound to 3 other carbons. Alright, and so delocalized electrons, I'm just going to save time, say that these can move throughout the graphite carrying charge. And carrying charge is conducting electricity. Okay, so that wasn't too much work. That is the end of question 5. Alright, so let's have a look at question 6. It says magnesium oxide nanoparticles can kill bacteria. And figure 6 is a graph which shows the percentage of bacteria killed by different size nanoparticles. Alright, so what we have on the y-axis is percentage of bacteria killed. Make sure that you don't think this is percentage of bacteria left. This is percentage of bacteria that have been killed. So for example here, where we are at 100, that means all the bacteria have been killed at this size of nanoparticle. Alright, so it says in part 1, give 2 conclusions that can be made from figure 6. Well, there are many answers to this. We can basically take our pick out of quite a large range of answers. The first one I'm going to say is if we have a look at the graphs up here, right, have a look at type 1 bacteria, which are the dots, and type 2 bacteria, which are the crosses. Well, at every single size of nanoparticle that we have on this graph, you know, after this graph it may carry on that trend and it will actually change. But at the moment on this graph, what we can see is that all of the type 1 bacteria are more susceptible to these nanoparticles than the type 2. So I'm going to say from graph, so when nanoparticles are less than or equal to 20 nanometers, type 1 bacteria are more susceptible, so it just means that they're killed easier, susceptible than type 2. Alright, so that's a comparison between the two types of bacteria. What else can we say? Well, if we have a look around about this point here, I can see that type 2 bacteria are 100% killed at this point, at this point, which is bang in the middle of 5 and 10, so that's going to be 7.5, I believe. Alright, and at this point, all of the type 1 bacteria are killed, and this, bearing in mind that it goes up in 0.5s, this is therefore 8.5. Alright, so I'm going to say that for nanoparticles, 7.5 to 8.5 nanometers, type 1 and 2 bacteria are all killed. Alright, now I can't say that lower than 7.5 they're all going to be killed as well, right? So to the left, I can't say that they're all going to be killed because we don't have any data for that. For some reason, maybe the really small nanoparticles aren't very effective and we don't have data to prove or disprove that. Alright, so let's move on to part 2. It says points are plotted for only some sizes of nanoparticles. Would collecting and plotting data for more sizes of nanoparticles improve the conclusions? Give reasons for your results. Or reasons for your answer, sorry. So that's obviously going to be a yes, right? More data gives you more reliable results, okay? So yes, more data would confirm or disprove the pattern shown. Alright, so the pattern shown, if we collected more data points, let's say I'm going to put the crosses, and they looked something like this. Alright, this would be very good, but if they look something like this, we'd say that, yeah, they pretty much fit the trend, and so we are correct. But if we had a cross which was maybe down here, and we had another cross down here which was there, and so on, right, we could say that maybe we just didn't pick enough data points, and maybe the relationship isn't as strong as we first thought. Alright, and so that's why more points is obviously going to be a benefit. So moving on, we have 6b. Magnesium oxide contains magnesium ions, so 2+ ions, and oxide ions, which are 2- ions. Describe as fully as you can what happens when magnesium atoms react with oxygen atoms to produce magnesium oxide. Alright, so let's have a think. Right, this is 4 marks and you're not marked on your English, which is fine. So, magnesium, let's think about magnesium first. Right, I'm going to do this in separate colours. So for magnesium, I'm going to actually use the red. Right, so I'm going to say that magnesium, or just Mg atoms. Alright, now magnesium is in group 2 of the periodic table. We know that really because we're going to form 2+ ions, but that means that it has 2 electrons, in its outer shell. It can lose those 2 electrons to create a full outer shell. So magnesium atoms lose 2 electrons. Right, I'm going to put in brackets here to the oxygen, just because that will be my point on the oxygen, to the oxygen to form Mg 2+ ions with a full outer electron shell. Alright, this is actually multiple points all in one because the magnesium atoms losing electrons is a point. The fact that they lose 2 electrons, this is per atom, right? So 2 electrons, I'll just put in here per atom, just so we're 100% clear, to form 2+ ions with a full outer electron shell. So now we've also stated that we've got full outer shells on our magnesium. So let's talk about the oxygen. I'll use green for the oxygen. All right. Oxygen atoms, I'll put each, just so we're clear, each gain 2 electrons. Right, I'm going to write from magnesium, just so we know where they've come from, to form O2- ions with a full outer electron shell. Alright, and now as a general point then, electrostatic forces of attraction are formed between these oppositely charged ions, which equals ionic bonding. Alright, that is more than enough for our 4 marks, because we've got the points about the losing and gaining electrons. We've said that 2 per atom on both, and we've also said that they form a full outer shell, and we've mentioned the ionic bonds, which is perfectly fine as well. Alright, so that is 6b. Let's move on to question 7. So it says that glass is made from silicon dioxide. Right, that's true. 7a says that silicon dioxide has a very high melting point. Other substances are added to silicon dioxide to make glass. Glass melts at a lower temperature than silicon dioxide. Suggest why. Alright, so there are a few things we can say here, but the main thing is that silicon dioxide is a large, giant covalent structure. However, if we add other substances, that means that that structure has been disrupted. So we can say that disruption of large crystal structure by other, oh, that's terrible handwriting, let's write that again, other substances. Alright, this does mean that they've sort of changed the bonds. There may be less covalent bonds due to the other substances being there, and that will also get you the mark. But this is absolutely fine, saying we've disrupted the structure. 7b, it says that sodium oxide is one of the substances that is added to silicon dioxide to make glass. Sodium oxide contains sodium 1+ ions and oxygen 2- ions. Give the formula of sodium oxide. Now all we need to do here is we need to balance the charges. Now if you think sodium, right, I'm going to say sodium plus and oxygen 2-. Now this is a +1 and this is a -2. Well, if I've got 1 and I take away 2, I get -1 overall, and that's not good enough, right? We need a neutral charge, we need a 0 charge, so I need to add another 1. 1 plus 1 is 2, take away 2 equals 0, which means that I've actually got 2 sodiums and 1 oxygen. So my formula is going to be Na2, because I have 2 of them, O. Alright, and that means that the charges have cancelled each other out. Whenever you're looking at the formula for a salt, the charges must cancel out and be neutral. If you have a charge on it, then it's not a salt, right? Okay, 7b part 2. Sodium oxide is made by heating sodium metal in oxygen gas. Complete the diagram below to show the outer electrons in an oxygen molecule. Alright, now you've got to be very careful here. So oxygen is in group 6 of the periodic table, which means it has 6 electrons in its outer shell. Now if it's forming a covalent bond, it wants 8 electrons in its outer shell. If it's forming a covalent bond with another oxygen, they both want 8 and they both have 6, right? So they both need to gain 2 more electrons, not 1. So we're not going to be sharing one pair of electrons. We're going to be sharing 2 pairs of electrons, which makes it a double bond. All right, and the best thing to do would be to fill that in first. So what I'm going to do is I'm going to use dot and cross because that's the convention. So I'm going to say that cross dot, that's 1 shared pair of electrons, but we need to share 2 pairs of electrons. All right, now the oxygen on the left, I'm just going to show crosses. Bearing in mind 2 out of 6 of its electrons are in this bond. It has 4 left, right? And I'm going to show them in pairs, like so. Okay, and then exactly the same, but with dots on the other oxygen. It's going to look like this. And that is your final answer. If you want, you can put O and O in the middle there. You don't have to, because it's already told you that they're oxygen. All right, next one. I just want to say that in the previous part, in this dot and cross diagram, I could have actually shown everything as crosses or everything as dots. The only reason is because they're both oxygen, right? So I could have actually shown that they're both the same atom by showing all the electrons as crosses or dots, right? I don't like doing that because it means that you could get confused as to where the electrons have come from. This way it shows you that definitely 2 out of 4 have come from the left hand side and 2 out of 4 have come from the right hand side, but you would have got the marks either way. Alright, so 7c, it says that glass can be coloured using tiny particles of gold. Gold is a metal. Describe the structure of a metal. Alright, so this is basically just metallic bonding. What does the structure of a metal look like? Well, if you remember, we have loads of regularly arranged metals. So these were originally atoms, but what they do is they lose an electron, so they all become positive ions. And the electrons, I'm just going to draw crosses, can move throughout, right? And we call these delocalized electrons. And so we have delocalized electrons in this structure, which allows them to conduct heat and electricity really well. Right, so let's just rub that out and let's start describing that. So metals arranged in a giant structure consisting of layers of metal ions. Okay. Next, each ion has lost its outer shell electrons. I'm going to put that S in brackets because if it's in group 1, then it's just an electron. All right. And these are able to move throughout the structure. They are delocalized electrons, and attraction between these and the positive metal ions holds the structure in place. Okay, right, and that's certainly worth 3 marks, right? We've mentioned the arrangement of the ions. We've mentioned the fact that they have lost their electrons. Those electrons have become delocalized, and forces of attraction. I could have said electrostatic, right? So here, just put a little arrow there. I could have said electrostatic forces of attraction, right? Hold the electrons and the metal ions in place. Well, they hold the metal ions in place. The electrons are allowed to move, but it's those forces which hold the metal ions where they are. All right, and that is the end of that question, and that is the end of the test. So I hope you're able to follow and that was useful to you. Please feel free to obviously rewind and go through the questions at your own pace if you need to revisit anything. But if you do have any questions on anything that I've covered, please feel free to comment in the box below or to send me a direct email. I'll be sure to get back to you. But please do, as usual, like and subscribe because there are more videos just like this coming very soon. But I look forward to seeing you in the next one.